Today you will be finding probabilities of events that are mutually exclusive using addition or multiplication rules, conditional probabilities, independent probabilities, and using two-way tables. Mutually exclusive. We say two events are mutually exclusive if they do not occur at the same time. This is also known as disjoint events. And notice if you look in the pictures, the picture on the bottom left, we would say events A and B are mutually exclusive because the events do not overlap one another, right? You have a green circle and you have a purple circle that they don't overlap. Whereas the picture on the right, if we see here circle A and circle B do have that dark purple overlap, we would say those events are not mutually exclusive. If we look up at the thinking bubble, we have some other simple results in rolling a 3 on a die and rolling a 4 on a die, right? When you roll a single die, it's not possible for you to get a face of 3 and a face of 4. So we say those events are mutually exclusive. For selecting a male student and randomly selecting a student who drives, we would say that is not mutually exclusive because you can be a male driver. So for the general addition rule, this is when you're finding the probability that one of two events occurs, or one of several events occurs. Typically, we will see the word or associated with it in the context. On your formula packet, this is the formula that denotes addition rule for probability. The U symbol just means the word or, so that says probability of A or B occurring. We're going to take the probability of A plus the probability of B and then subtract the probability of both A and B. The upside down U is and, okay? So that P of A and B just means that those events occur at the same time. Now, if the events are mutually exclusive, it is 0 because the circles do not overlap. So notice we're going to take all of event A, we'll subtract event B, or we'll add event B, and then we'll take away the stuff they have in common. So in our first example, we have police report that 78% of drivers stopped on suspicion of drunk driving are given a breath test, 36% a blood test, and 22% both tests. What is the probability that a randomly selected DWI subject is given a test? Okay, so for me, if I know that I see critical information here, like I have both tests, suspicion, we have breath test, and then we have blood test, and then I see both. Sometimes what helps me is to draw a Venn diagram. So we can say event A is the breath test. And that means event B is the blood test. Now, because we have 22% have both tests, we have overlap. So you would draw your two circles, and the overlap is where I would start my Venn diagram, 22%. Okay, so now I know that entire event A is 78%. But notice we have that 22% already represented in the diagram. So if we take 78% less 22%, we do get 56%. And we'll do a similar process for the blood test, right? If I know blood test is all of circle B and 22% is already represented, we just take our 36 minus 22. And to find the whatever's left over, if you take 56 plus 22 plus 14 and subtract it from 100%, it does give you that 8%. So to answer a question about the probability of a test, right, we're just going to add our 56.
The next question states a blood test or a breath test, but not both. Okay, so for this question, what we would do is we would take our breath test proportion plus the percent of a blood test and not both, so I ignore that overlap. Okay, so our answer is the 56% plus the 14% or 70%. And for neither test, the neither test, that would just be this 8% we found earlier because they are not in the circles.
Okay, so next example, we want to find the probability of randomly selecting a queen or a king from a deck of cards. Well, couple key items here. Notice we see the word or. That tells my brain to add. And I'm finding the probability of only one event. So before the word or is queen, and we know there are 4 out of 52 of the cards are queens. Or means to add. And then after the or, we see king. Again, there are also 4 kings in the deck of cards. So we would do 4 over 52 plus 4 over 52. And because you have no deck that is a queen and a king, or a, I guess, queen, they are mutually exclusive. So we subtract 0, and we do get about 15%. If we look at the next problem, we want to find the probability of selecting a queen or a club from a deck of cards. Again, notice we have that critical word or. That tells my mind I'm going to add. So before the word or is queen, and as we stated earlier, we have 4 out of 52 cards that are queens. Or means we're going to add. After, we have clubs. So we have 13 clubs in a deck of cards because it's a quarter of the deck. Now, the next part, you have to ask yourself, do you have a queen that is also a club? And you do, and you have to subtract that overlapped card, 1 over 52. And you do get 16 over 52, or 4 over 13, or about 31%. Okay, for the probability of A but not B. If we find the probability of A, we can subtract the probability of both of them occurring at the same time. Okay, so notice in our box here, we have the probability of A and not B. I take the probability of A and subtract the overlap. So here's a simple example. The probability of obtaining a king, but not a heart. Okay. I would take 4 out of 52, because that's the number of kings in the deck, and I would subtract the king of hearts. So we would have 3 over 52, or about 6%. Okay, so conditional probability. This is a probability with a given condition. Usually what it happens is it alters the total possible outcomes in our denominator. So this is what it looks like, probably on your formula sheet would be my guess. So the probability of B slash A, meaning the probability of B given that A has already happened, is going to equal the probability of A and B over the probability that A has already happened. Okay, so in our next example, we want to find the probability of drawing an ace given that it is a heart. So if I know for certain already the ace is a heart, right? I know this is a heart. I have 13 hearts in the deck, and of those hearts, one of them is an ace. If we look at the next simple example, notice find the probability of drawing a queen given that it is a face card. Well, if I already know it's a face card, remember faces are jacks, queens, and kings, and there's 4 of each type. So we have 12 faces, and 4 of those are queen. Okay, so as we move on to independence, the first event does not affect the outcome of the second, okay, in a sequence of events. However, dependent events do affect each other. So if I select a king, then a queen with replacement. So notice in this first one on the left, we're selecting a queen, which we know to be 4 out of 52. Then we're going to shift over and we're going to select a queen with a king chosen and replace. So it's like I pick up the first card, it's a queen, and then I put it back in the deck. What's the probability of obtaining a king? Well, it's going to be the same, 4 out of 52. So because these probabilities match, we say these events are independent. Let's look at another example. Let's say we're selecting a queen again. So We are selecting a queen, and notice we do have a probability of 4 out of 52 again. And for our other event, notice we're selecting a queen with the king chosen but not replaced. Okay, so it's like I grab the first card, it's a queen, but I keep it, I don't put it back in the deck. Well, what happens to our probability of obtaining a king? Well, it changes. So because of this change, we say these events are dependent. Let's look at another one. Let's say we toss a coin and obtain a head, and then roll a 6-sided die and obtain a 6. So we know the probability of us rolling a 6 is just 1 over 6. Okay? If I want to roll a 6 after getting a head on a coin toss, that is still 1 over 6. So these events are independent. Okay, so our examples lead us to the following conclusion. Events A and B are independent if and only if the probability of A is the same as the probability of A given that B has already occurred. Okay, so this statement has to be true, and this is big on FRQs, on the AP exam. It shows up, at least it has in the last several years. Okay, remember I'm saying the probability of A equals the probability of A given that B has already occurred. When we talk about the multiplication rule, remember you're doing a probability of a sequence of events. Typically it has and in the context or a comma that implies plural. In other words, you're finding the probability of more than one event, and we multiply. So if we want to find the probability of drawing a king and then drawing a queen without replacement, okay, without replacement means I keep the card and I don't put it back in the deck. So what we would do here, that first fraction, what that represents is us obtaining a king, and we know there are 4 out of 52 cards that are king, and I keep it. Okay, so if I want the second card to be a queen, that would be 4, and then how many cards are left in the deck? 51, and you would just multiply straight across and get about 0.006. If we look at the next example, if we want to find the probability of drawing a heart and then drawing a club with replacement, the probability of us obtaining a heart is 13, because there's 13 over 52, or 1 over 4. And then if I put that card back in the deck, us drawing a club is going to be the same. Okay, so 0.0625. Let's get a little more complex. So we're dealt 4 cards. What is the probability that your first face card is the last one dealt? Okay. Okay, so the first face card is the last one dealt. So let's do a little bit of thinking here. I know the last one is my first face. Okay. These numbers represent cards without faces. And these numbers represent cards left in deck. Okay, so I would do 40 over 52. I keep that card. The next card would be 39 non-faces over 51 because we took 1 card away, times 38 out of 50 because it's the third card, times 12 over 49. Next problem, you are dealt 4 cards. What is the probability that you have at least 1 club? Well, remember with an at least problem, it's a little strange, right? I want to do the opposite of what it says. I know an at least problem means I'm going to do 1 minus the probability of no clubs, right? If I don't do it this way, I have to find every possible combination and add the sequence together. It's just much easier if we take 100% minus the opposite of what the question is asking, right? So at least 1 club means 1, 2, 3, or 4 clubs. I don't want to go through the effort of finding all the possible combinations. So we're just going to subtract it from 1 minus no clubs. So these numerators represent cards that are not clubs, and the denominator represents cards without replacement. And you do get an answer of about 70%. I want to know, what is the probability that a child has a high IQ? So I take my total high IQ, right, here's my high IQ. So I'm going to take the 52 over the total number of kids, and we get about 50%. Next example, I want to find the probability that a child has the gene present. Okay, so total gene present is our 72. And if I want to know probability that a child, total children, is 102. So 72 over 102, the end. Next question, we want to find the probability that a child has a high IQ given that the child has the gene. Okay, so this one's a little different because we already know that the child has the gene. So gene present, 72, and has a high IQ, 33. Okay. And I believe here is our last one. Notice that it says find the probability that a child has a high IQ and that the child has the gene. Find the probability that a child has a high IQ and has the gene. Okay, so 102 is our denominator, right? And then our numerator is just going to be the high IQ and gene present box, 33.